Science.
This is episode 5 of Physics Astronomy Guys. I'm Alan.
And I'm Ian. This is a show about science.
To start off today's episode, we're going to answer the viewer question from last episode. And that was, obviously an ant has far less surface area than a human, so they would be encountering far less wind resistance as they fall through the atmosphere. Yet, why is it then that an ant has a much lower terminal velocity than a human? And the answer is terminal velocity is defined as the point at which the downward force of gravity is canceled out by the upward force of air resistance. Well, for an ant's mass is only about 1 milligram, so it weighs far less than a human. So in order to counter the force of gravity, the wind resistance has to be far less. And because as you increase something's size, mass goes up cubically and surface area goes up squarely, an ant, the ratio of surface area to mass is much greater than for a human. So it takes far less speed, so it has to push through far fewer atoms in the atmosphere in order to cancel out the weight of gravity. And it actually so happens that an ant's terminal velocity is not fatal to an ant. So you can drop an ant from any height and it would survive.
Yep, and nobody answered that. So
But if someone does answer it before we can get this video imported,
we'll put it on here because we're just going to put an annotation on. And so we'll start out this week's episode with our current events.
But first, we had a donation from our physics teacher.
The donation was this whiteboard.
So,
as you have saw.
So, we'll use that in today's episode.
We'll use that throughout all the episodes so we can write equations on it, draw diagrams to better visualize what we're talking about. And so, you can put your party hats on because the shuttle missions possibly may go on until 2017. USA plans to continue the shuttle program. USA standing for United Space Alliance, not United States. And so they're planning on funding the Endeavour and Atlantis shuttles to keep flying through 2017, giving them $1.5 billion a year. And so we can hopefully look forward to more missions.
And also, the Ares rocket is going to be recycled. Some of the parts are going to be used, or most of the parts actually are going to be used in building the Liberty rocket, which will stand 363 feet tall. So they're going to be using old parts from a older space shuttle.
And I think they're using some technology that out of the space shuttle and out of one more rocket. I can't remember the name. But that's going to be, I think, replacing shuttles possibly sometime in the future. And so we will move on to our topic of the day that we choose, which is today, Alan?
So today we're going to talk about how astronomers can find planetary systems around other stars.
Very carefully.
So one of the most important things you know in order to calculate for a planet is you need to know the star's mass. In order to do that, you have to know the brightness that you see on Earth, which we can just look at it and tell. And then you also need to know how far away it is in order to calculate its actual brightness. And then based on what stage in its life it is, you can determine how large it is. So the way astronomers calculate how far away a star is they have to look at it at different points in the air. I'm going to draw a rough little thing here. It won't be to scale, but
no.
So imagine again, not to scale at all, if you can see that. You've got the you've got the sun right here, and here is where Earth would be in January, and here is where it would be in July. And then if you have a star, say right about here, that you're looking at, and then you've got background stars over here. If you look at the background stars from January, your line of sight is like this. But if you look at it from July, your line of sight is like this. So you'll notice from January, there's a different point that the star looks like as compared to the background stars. As from July. Here, July, you're looking up, and January, you're looking down, or whatever direction the star may happen to be. And given that we know the distance to the sun, 1 AU, between January and July would be 2 AUs, or about 187 million miles. So then, given that it's 187 million miles, it's just simple trigonometry to determine the distance to this star given the change in angle between where the background stars appear to be. Okay? So that's how we calculate for the mass of the star. And the reason that that's important is because in order to determine the mass of the planet and how far away it is, you need to know the gravitational attraction between the planet and the parent star. Given gravity is gravitational constant times mass of one body times mass of the other body over radius squared. And then for gravitational acceleration, you just cancel out the smaller body's mass. You need to know the mass of the star. Well, if you look at the star between January and July, of course, because of that shift, we call it the parallax method, you'll notice there's a slight resonance there. But then if it's a planetary system, there will also be another resonance in that resonance, because as the planet moves around the parent star, it tugs on it a little bit. So there's a slight wobble. And if you look at where the wobble is on one side and then where the wobble is on the other side, and you know the time distance in between there, then you can know the orbital period. And if you know the mass of the body, and therefore you know the gravitational attraction, once you can calculate the distance, you can also find where that radius is, such that the centripetal force would be equal to the gravitational force. Given centripetal force is omega r, and then, of course, gravitational force, I already said, your only variable is r. So you can use simple algebra to determine how far away the planet is and the mass of the planet.
Okay, and this is our final piece of the viewer question that was submitted a while back. We're going to finish with the Apollo missions, but since the Apollo missions are more in depth, I guess, a lot more stuff happened on them and they're slightly more interesting, we're going to have different sections of videos, so like we'll have an ending to each one instead of just splitting it and then posting another part. We'll just
so this is the end of part 1 then, and come back for part 2.